Okay, let's get started. Good morning, everyone. We are glad to have Professor Mauricio Romo from Siemens and Siemens Fudan University. He will present non-commutative resolutions of Calabi-Yau singularity double covers and mirror symmetry. Let's welcome.
Thank you very much to the audience for attending, and also thank you very much to the organizers of this important congress for giving me the opportunity to give a plenary talk. Thank you. I have enjoyed a lot many of the talks here. First things first, even though they should be last, but first. Since I'm one of the organizers, at least on paper, officially I should invite you to come to Strings 2026 next year. So if you are around Shanghai or if you want to come, please come. I mean, I hope we have a very great workshop there, very great Strings, another iteration of Strings. So, okay. That's part of my administrative job. Now I go to the serious stuff. So we are going to talk today about non-commutative resolutions of Calabi-Yau singular double covers and mirror symmetry. This is based on two papers. These are two preprints that are with a subset, both are with a subset of this cardinality tree set here. Okay. And we have work in progress also with them. So outline, so what I'm going to talk about. So because the audience is very diverse, probably we are only going to do the first part of this outline. So first I have to tell you kind of the motivation of why we look at this non-commutative resolution, and the motivation is a conjecture by Hosono, Li, Lian, and Yao from 2020. So this will be HLY. So they have a conjecture, which I'm going to explain in detail. After this conjecture, I have to tell you how the tools from physics, which is gauge linear sigma models that I guess in this audience are many experts models. So this GLSM, how the dynamics or the physics of GLSMs allows us to construct non-commutative. This will be non-commutative if you want non-commutative. So NC resolutions of these singular double covers. So that will be second part, and then I'm going to tell you how these two comes together, and how with the use of some open correlator in GLSM, also known as the hemisphere partition function, which I'm very fond of for obvious reasons. We can kind of build more evidence. There is evidence for the HLLY conjecture. So pretty much probably I will manage to do up to here, which is kind of up to this first paper. If time allows, which is very unlikely, but if time allows, I can tell you some generalizations that you can do if you have this physics, and these generalizations appear in this paper. But let's concentrate on this, because at least if I can communicate the message of these first three, is already very good. So I need to talk about this HLLY conjecture for mirror pairs. So which pair of Calabi-Yaus we are talking about? And what is the conjecture? Yes, it's from 2020. So I have to say this talk is very old-fashioned. It uses a lot of 90s mathematics and 90s physics. So if you're a person from the 90s, you should be able to enjoy a blast from the past. If you are young, well, maybe you should learn these things. Okay, so let's consider P delta. So what is P delta? We are going to consider a projective toric. Uh, oh, it's, where should I put the mic? In the middle of myself. There, completely symmetric. Okay, no problem. Thank you very much. Okay. So this is going to be a projective toric Fano variety, which we are going to assume is smooth, or assume, for this talk it's better to assume it's smooth, even though we don't need this to be smooth. We can generalize, or you can assume it accepts some toric desingularization, okay? But let's assume it's smooth for this talk. So why is P delta? So projective toric Fano can be defined by a fan, is defined by a fan, sigma delta, usually inside some lattice that you call N and R, which is like some lattice N. So R of, I will fix the rank once and for all to be set N. A fan what that you obtain has that's the normal cone, is the normal fan of reflexive polytope in this dual. This is the dual of this, okay. So this is a reflexive lattice polytope. So yeah, there is a lot of, there is some toric language and terminology here that maybe some of you are not too familiar. I'm not a big fan of toric stuff, I have to admit, but I have to use it in this part. But believe me, it's not going to be, I'm going to also do some examples, hopefully. So you can imagine projective space, any toric Fano that's defined that way. And you consider the following. So E1, you write it like this, is a collection of divisors. These are divisors that add up this to the anti-canonical bundle of P delta. So this is the an F partition, Okay, so with this data, so we are going to write this data as this. I'm going to just use this symbol to talk about the F partition. So F partition, I will indistinctly go between, I will be a bit sloppy, I will always, F partition can mean divisor, but it can also mean, EGA can mean line bundle over P delta. Okay, that's the usual for these cases. So I will use the same notation, that's what I mean. For E, like if it, I mean it's a divisor, if I mean it's a line bundle. So many years ago, so Batirev and Borisov tell us how to get another reflexive Fano, another toric Fano, which they call Pinabla. They give us tell us how to get a pair, Pinabla Fa, which is and also toric Fano, which we also can assume is smooth. And this delta is constructed from the dual polytope of delta. And this is a dual, what they call a dual Neff partition. So given an F partition, so they tell you how to build from this data this pair. If you have the pair EA and delta, you can build a pair nabla and FA. Okay, so this was this was the work of Patrick Borisov from many years ago. And their theorem is that the Calabi-Yau complete intersections of generic sections of generic sections of FA slash EA inside P nabla slash P delta are mirror pairs. So that's the original theorem of Borisov. They are mirror pairs I mean, they depends what you call mirror symmetry, okay? So at least at the level of Hodge numbers, like the most elementary mirrors that you can imagine, these two pairs are shown to be mirrors. So that's just reminding you of some very old piece of mathematics. So what happened here, so now we go to many years after this. This was kind of in the 90s, I think. So we jump to this HLLY. So what they did is like they consider, instead of considering these complete intersections, this HLLY, they consider a singular double cover. So they consider Y. So it's a double cover over P delta branch over a product branch over S equal to 0, where this is a product of product is K equal 1 to R. This R is this R, where SK is a product, or takes a product form, SK1, sorry, times SK2, which is a section of P delta comma 2. Okay. And it's and such that for this product is in the form that this one is generic section of EK, and this one is a monomial. So the divisor associated to xk1 is actually EK. So this means essentially one is a monomial and the other one is a generic section. Okay, so let me do one. So for example, you can have the SK is sections of 2 EK. Yeah. So each section is you impose that is a product. It's not a reducible. It's reducible. Each SK is a section of 2 EK. Yes, that's condition for this 2 Calabi-Yau. I will write an example. There are sections of EK. Yeah. This by definition and this because I impose. Yeah. Yeah, that's 2 EK. Oh, very good. So for example, if it's P2, one possibility, so this is the one possibility if you take an F partition an F partition that is like H plus H plus H. I'm denoted it like this way because all the divisors are equivalent. So let's write it like this. Then Sk, like if the coordinates here are x1, x2, x3, homogeneous coordinate, then for example, S1 is x1 times a line, it's a line. A generic line, and S2 is x2 times a generic line, and so on. That's one example. I'm not going to write S3, okay? So that's one possibility. So given this, why? Because of this kind of strange condition, the reason they impose this strange condition is because it looks strange, but the reason they impose this condition is because that gives them a lot of control over the complex structure of this variety Y. So this condition of being a product, this condition here, this condition, they call it in their paper gauge fixing condition. The fact that it's of a product of this form. Don't ask, if you are a physicist, that gauge has nothing to do with any gauge you are familiar with. It's just mathematicians' terminology, right? I mean, that's happened when a paper, it has only mathematicians on the others, right? They start to use this strange name that looks like physics, but there's nothing to do with physics. But it's okay. I mean, it means they have fixed the action of some group, okay, on this generic branching loci. That's right. I can discuss it after the talk because it's recorded. So, okay. So let me say one thing. Okay, let me write it here then. So now you can see that we can mimic, right? We can mimic this mimic by considering something I call Y check over the nabla, also double cover, and use here this branching loci with the branching loci. The branching loci that in this case, I don't know, you can call them Fk, where the Fk are defined, the Fks are sections now of 2Fa, 2Fk. So in this case, so this is the branching. Sorry that it was a bit messy there, but you can see that you can mimic the same construction within this form, with the other pair, with this pair. It's exactly the same. So the conjecture of this HLLY is that both of these form a mirror pair. So the conjecture of HLLY that I was referring at the beginning is that Y check form a mirror pair. We can mimic the construction above. So you can do this, what I did for the construction. I use delta, which defines this funnel, and the Neff partition that defines this branching loci. In this case, it defines a branching loci. So with that pair, I can construct always this double cover. So here I just do the same, but with this pair. So yeah, for saying that doesn't sound that surprising, but it's very interesting actually. So this form a mirror pair. That's the conjecture. So very good. So the evidence, so far the evidence for this conjecture, so the evidence in that paper is a proposition. So the proposition that they have, let's see if I have here, yes. So the evidence is a proposition from HLLY. They find that HPQ, so they find that chi topological y equal minus 1 to the n chi topological of y check. Okay. So that's the minimal thing you will ask for a mirror, right? And this implies for n less or equal than 4, this implies that actually HPQ of y is Hn minus b over q. Okay. So that's the evidence. So that's the most old-fashioned mirror symmetry statement you can make. But it's an interesting statement. Why? In particular, it's interesting because, well, nobody have considered before this, even though it looks like a very natural construction. But in addition, as I mentioned, and it's in the title, this y and y check are incredibly singular in general. For when they are dimension 2 or higher, these are singular double covers, like you can compute them very explicitly, so you can check maybe if you are bored, and you will see that they have singularities. However, so remark, maybe we put a remark here. Look, I'm not going to erase it, so the remark is that y and y check have singularity, have at most, or often, let me put it this way, all singularities, yeah, actually, singularities are of quotient type by some finite group. Actually, in the second paper, we make a much more precise statement than this, and we show that you can write them actually has a global quotient, but has a global quotient of a complete intersection, not a complete intersection in a global quotient. Those two phrases are different, okay? That's your exercise. So, right? So just write it like this. Write y. You can write y has a hypersurface in weighted projective space, right? So you write in this example y like this, y squared equals, right, product from I equal 1 to 3, xi, li of x, and you compute the Jacobian, right? That's very good. Yeah, you can tell me at the end of the talk. You can show me your solution, and we'll check. Yeah, well, the important thing is they are Calabi-Yau. From there, you can see very easily they are Calabi-Yau, and the singularities. Yeah, you can kind of believe it because the branching loci is so degenerate. It's like in this case, it's not just if it was a generic sectic, then it will be smooth. But it's not a generic sectic, it's highly non-generic, right? But they claim even if you consider this, all singularities are of this type, which can be made even more precise, but all singularities are of this type, and therefore we can, and that they also do on a follow-up paper, I think with Kosono. What they do on another paper in a follow-up. Because of this, we can compute, and this is kind of how they got inspired, I guess, to formulate this conjecture. That's on the paper. We can compute the periods of y. or white check, it doesn't matter. Explicit. Okay? So when I say periods, I mean literary periods. You take gamma in a Hn, or gamma like this in a Hn of Y set, or Y check, and then you compute pi gamma is the period, this is the period. It's going to be this, right? That period is a period of gamma. Period. So this can be computed explicitly. I'm not going to do it, but you can compute it explicitly from this data because it's so degenerate and because of this gauge fixing condition that allows it. Yes. Yeah, they do kind of the opposite, right? They first explicitly compute that, and then from that, that's what I'm going to say next. They can deduce, because you have this explicitly, without the, yeah, it's not like they have a differential equation, they solve and they get this. No, they compute this and then they get a differential equation. So that gives you something called Gelfand-Kapranov-Selevinsky or GKC system, which if you are not familiar, try to ask me, but it's very long to define and write here. But for the people that are a little bit more familiar with this story, you can think in this case of the GKC system has equivalent to Picard-Fuchs equation. This is not true in general, but in these examples it happens to be. Only in these examples, okay? Picard-Fuchs equation. So this GKC is a system of differential equations. Please, Slava. That's right. That's right. These are to say it more explicitly, it's just I didn't want to write too much, but let me say it for you. So what you do is you build this from this data. So which parameters can appear here? The only parameters that can appear here are the coefficients of these sections. Like in this case, it will be the coefficients of these lines, for example. But there is redundancy on those coefficients because of some rescaling of coordinates, etc. So what you do is at the end, when you get rid of this, of this redundancy, this period depends only on certain combinations of these coefficients, and that's the Picard-Fuchs equation. Okay, and if you write the equations on all the coefficients, there are also some differential equations that look simpler, but in more variables. Those are the GKC equations. So in this case, it's very easy to go from one to the other. But in general, that's not true. Yes. No, it's okay. No, they are all singular, all the way. That's correct. They have to use, yeah. That's right. That's why it's a math paper. Otherwise, if it was everything smooth, like it was all done in the, I don't know, in the 20s. So. But in this case, yeah, they have to use some orbifold cohomology, but because of this, you can use tools that are, no, like, yeah. All right, so that's what they did. And they have this GKC system that I can write like, maybe I will use a symbol like G, but then K and C get angry. So maybe how can I call the GKC system? A GKC system called, I will call it M of Y. Or Y check. So that's the title for the GKC system. Very good. I just reviewed your conjectures, so you haven't missed anything. Your conjecture with Hosono and Bong and TJ. So yeah, as expected, no, I can tell you how the physics become useful, how physics become useful in this problem, and that's what I'm going to tell you next. Let me talk about this. So now you have a puzzle of a question. Puzzle. So the puzzle is if, let's say, you have periods, if you have y and its GKC system. This, I don't know, this is my notation for GKC system, or M of y. This is the GKC. So you have, then you have the periods of y, like this one. And you can ask the question, if you have now this proposed mirror, so this mirror, which is another singular double cover here, with some GKC, with its own GKC system, but I'm only going to use this GKC system on that side. You can ask what's the mirror of that, right? So what's the mirror of the period? So this is the period. So we call it a V period because it depends, has parameters only on bulk like V-type deformations, only on complex structure. And here you want to compare this by mirror, you may have something here what is called something that will be a function of the class of some sheaf. So this E will be in EV4 in principle of Y check, and it will be the mirror of whatever A brane corresponds to this. So this will be this, where this E check, the mirror of this gamma, is this E, has charges, and this is what we call an A period. So in principle, and in particular, this A period will depend, it's called A period because it depends on the color or symplectic deformations of this Y check. Okay, it depends on the symplectic, we can include Y check here. It will be on the symplectic deformation of this Y check. So in particular, one of the properties that should be satisfied by this A period particular, Y annihilates, right? Because I put an equal sign. Pi gamma of Y Z Y check comma E. For all gamma and E. Up to a change of coordinates, which usually we call the mirror map, but up to a change of coordinate, the same differential equation should be satisfied by this. That's all that I'm saying. So, how you can compute, since you have a singular variety, now if you are going to compute something like the A period, meaning the central charge of a V brane for physicists, working with a sigma model with target space, a singular Calabi-Yau is not going to cut it. You need to do something else. And that's where the non-commutative resolution enters. So, proposal, let's say proposal to compute Z of, here you can put Y or Y check, but I will keep Y check just not to overly confuse you, but because both are the same nature. Proposal to compute this is use a non-commutative resolution let's say implemented by a gauge linear sigma model. So the next, since we have like 15 minutes or so, what I'm going to do is going to construct this non-commutative resolution step by step for an example, in order not to overcrowd this board with notation, I mean, or an example or a family of examples. So in order to make our life easier and the notation easier, sorry? My is differential operator. It's a collection of differential operators. It's like the GKC system. Yeah, sorry, maybe M of y was not the best notation. Okay, so do it in an example. So for example, best to use is P delta or P nabla. Let's say P nabla since we are in this side. P nabla is going to be Pn. Okay, just Pn with coordinates x1 to xn plus 1. And branching loci is given by is going to be defined by the defined by the Neff partition 1 H R H. So what you need is for it to be an F partition is an F partition of the anti-canonical bundle of this guy. So what you need is these coefficients here, 1 to R. This has to sum up to m plus 1. So these are positive. Each of the i's are right. They are positive. Positive in general, strictly positive. So that's my Neff partition or my Neff divisor. And now, how do I build the non-commutative resolution? So first we define what is called a set-2ger over n. So this is a fancy word, but it's just the following variety that I call Pn tilde, which is defined as a symplectic quotient, as a geometric quotient, as Cn plus 1, mod, if you want like this, mod C star, right? Where this start act with weights 2, 2. So these are the weights of this action. So this is a homomorphic space to Pn, which is just Pn with all the weights doubled. Okay. So I call it P tilde just to distinguish between this and this. Tilde. Oh, the Z2 is because there is a trivial Z2 subgroup of this C star acting. So they are homomorphic, but what I'm going to use is I'm going to use line bundles over this P tilde. And the line bundles of the space of line bundles over P and P tilde is different. Because here I can consider line bundles with fiber acting with weight 1, which will be something like a 1/2 here. So it's different. These two spaces, the space of line bundles of these two spaces I wrote is different. But as a space, as a topological spaces, they are homomorphic. That's correct. Okay. Yes. Yeah, this is this double line. It's exactly identical. It's identical. It's just the weights are double. So for at this stage, I have done nothing. I have defined some useless thing, but I'm going to make a use of it. So we define, since this is a physics talk, I have to say we define a GLSM with matter with the following matter. So with the following matter, so this will be a U1 GLSM. So if you have, so how I write this? So the U1 weight, so we have these guys, fields that are going to correspond to this Xi, which will have U1 charge 2. And I'm going to have Zi, kind of equivalent to this, which are going to have a gauge charge -1. And I'm going to include, because now I'm going to include set A, let's say set A prime, which charge minus dA. Okay, so this is very down-to-earth construction for if you're familiar with GLSM. So besides that, I have to tell you what's the superpotential, right? So the superpotential for this GLSM and superpotential to the superpotential has to be gauge invariant, right? So the superpotential is going to be something very simple, like 1 to n plus 1, set I squared, x tilde I, plus sum over A from 1 to R, set prime A squared, times the section corresponding to each of these t, right? So here the branching loci is defined by this section, so I will write it like this. So in the previous notation there is a 2, but I'm going to write F2, Fa of x tilde, So remember that I will just remind you that this Fa were sections of over Pn of the line bundle of the A. So I can trivially push them forward to sections in P tilde. They just double the weight, right? So I can write this, and this is gauge invariant, so it's good. So yes. It's not generic. It's not generic. Oh, I will tell you right now. But you know the motivation. I don't know if I will answer something that you expect me to say. No, the motivation is the following. So what is this? This looks like a Landau-Ginzburg model. So since that was the question, so motivation. Time is pressing, but I'm getting to make the statement I wanted to make. As you see, we didn't do the generalizations, but motivation of this is you can consider this pair, you can consider W and this P, and you can see, so this is very physics, this part is not rigorous, but you can think of this W over this P tilde N as a family, right? It's a family of massive Landau-Ginzburg models in C m plus 1 plus R, with that the set prime, right? Is coordinate. So these are the fiber coordinates. So this, if you fix x tilde, this is like a massive Landau-Ginzburg model. But is it really massive? Well, no, because it's massive except at certain special loci. So except at loci where the mass matrix is of reduced rank. And where is that loci? Well, it's diagonal, so you can compute it yourself, but even though it's a homework, I will do it for you. So this is when product I equal 1 to n plus 1 of xi tilde times all these coefficients, right? Pi equal 1 to r fa of x tilde equal to 0. So if you go back to the branching loci I wrote for the double cover, for the singular double cover, with the special choice of this gauge fixing or the special choice of complex structure, if you want, is exactly this. So that's the motivation behind. So yeah, for these. But this is linear. This is linear. This is linear, and this depends on your choices of D. And also the X tildes are like, they live on this kind of base manifold. So they're kind of, they're coordinates on this base manifold. So for example, they cannot be 0 at the simultaneously, etc. But it's true, you can also think maybe in terms of the X tilde, but if you think in terms of the set, you reproduce what you have before. So like you reproduce this. So they claim, yeah.
But I guess if you reduce, then it will be
Different, yes. You can, I mean, if you don't like to think of this detail that has double weight, etc., you can kind of rescale the weights of this U1. You can kind of divide by 2, but you have to remember then that you have some set 2 action.
Oh, sure.
Yeah, and then this becomes like 1/2, meaning like -1 plus some non-trivial action of the Z2. The addition of Z2, you mean acting on this little set? You mean as Z2, that this is Z2 symmetry acting on these sets, right?
Then you earn additional C2 1. But I guess you are including.
This is an old-fashioned talk, so you are not allowed to say the words generalized symmetries and these things that young people do, like higher form. There is a no, okay. There is a symmetry here, which is a Z2 that acts with the same weight on all the sets. That comes from this. That comes from these two, because that Z2 acts trivially on the X tilde. That one is a quantum symmetry, if you want. Symmetry. It's like an orbifold. It's orbifolded. You also have additional Z2 that are like flavor that acts on these Zs separately. But I'm not touching that. They have a meaning, but we don't have time to talk about that meaning. So let me, in the last 2 minutes, give you some statements about consequences of this. Okay, that's which is the claim of the first paper. There is something like that behind, yeah. There is something like that behind. There is a more geometric interpretation of this. But that geometric interpretation, as far as I know, only works on some special cases. I don't know how to generalize for... Here I give you an example with PN base. But in general, if you have like a toric base, I don't know how to work out that. But yes, there is like some non-trivial B-field in the background. But the words I said are completely kind of self-contained. It's this family of Landau-Ginzburg model. This is a smooth model. This is a smooth SCFT. It has no problem. So the claim is there are various claims. So one is that using hemisphere, the so-called hemisphere partition function, which is this open correlator I was talking about. So if you are not familiar with it, which probably you are not, which is something we create we compute with Hori in 2013. It is equal, this you can compute for this model, this you can compute of this model. It's an hemisphere, it has a boundary, so it requires a boundary condition, so it requires a boundary object, which B belong to the matrix factorizations, U1 matrix factorizations of, if you want, of this space. So in this case, don't forget all this U1. So it's matrix factorization in some variety B of this W. So this variety B is like this variety B is line bundles. I'm not line bundles over this P tilde n. I didn't write it explicitly, sorry. So the boundary condition is determined by this object here in this category of matrix factorizations. So this hemisphere partition function, given a boundary condition, equals the B periods of, in this case I call it Y check, so I should call it with Y, which is the proposed mirror of Y check by Cosono, Lian, Li, and Zhao. And this is one thing this is one claim, so this is kind of a conjecture. And the second is that the second is a theorem. The second is a theorem is that MY check, so this, remember this was the GKC system annihilates, I mean this is like evidence for this one, right? Annihilates. This is like the evidence, this annihilates so we can call this set D2 disk for any sphere of P. So this annihilates set D2 of P after you have identified appropriately the physical variables with the GKC variables. That part of the theorem. And maybe to finish off, it's 32. I'm already past. 3 minutes, okay. Don't worry. I mean, I'm going to make just a last statement. So this is a last statement. Maybe it's a kind of a remark that, so this is going to be a model for the derived category of this non-commutative resolution of Y. But if you don't like it, there is another way of seeing it. So this MFYW, you can also see it has this derived category that I'm going to explain in a second. DV in this case is P tilde, okay? P tilde n, but you can do it more general. P tilde n, comma CL0, which this thing is the derived category. It's the derived category. It's a lot of words, okay? Of chiefs. Sorry, chiefs of CL0. I will say what is CL0 modules over Pn tilde. Sorry. This you remove this. You can remove that. It's not Pn, just Pn. And what is CL0? And CL0 is even parts, is so-called even parts of a Clifford algebra, It's a Clifford algebra defined by the following quadratic form, and with this I finish. So by the way, this theorem is in LLR, so this thing in our 2023 paper. So Clifford algebra defined by the quadratic form. So it's a quadratic form over P tilde, over Pn. So for the quadratic form dW, this set A, set B, like the Hessian, it's the mass matrix. So it's the mass matrix. So this is my quadratic form A1. So you can see it's a quadratic form, fiber over the n. So it has a function of x. Okay, so that's it. Thank you for the patience. Yes. No, so the V period had nothing to do with Romo-Bitten invariance. No, it's completely independent of Romo-Bitten invariance. The V period is a purely classical thing, like the one I wrote. The V period is an integral of the holomorphic top form. The A period depends on genus 0 Romo-Bitten invariance. But they are equal. So usually what you do in practice, for example, in these old-timer papers, you compute the V period because you can compute it classically. And then if you know the mirror map, that's it, that's the A period, even if you haven't computed anything. But you can read from there the Romo-Bitten invariance if you know the general form.
Yeah, Sam, you wrote down, for example, this 2 P7. I want to ask, this model always flop to a smooth complete intersection in the weighted Pareto space?
Good question. Very good question. No, in general, no. That's a very exceptional case.
Do you have an example? Not limited to freeform.
So we can do P3 with branching loci. Choose a branching loci over P3, right? And do this thing, write this GLSM I told you. So if you choose P3 and you choose the branching loci, the collection of lines, like 8 lines, you are going to get in the other phase P7, 2, 2, 2, 2.
Yes, sure.
But take another branching loci, also singular. So all this thing goes through, or all this thing is non-trivial. Take the branching loci, let's say something like a sextic and something else. I mean, a sextic and a quadric. Or you can also take a more degenerate, like a collection of 4 quadrics, something like that. Do the same procedure, and you go to the other phase, and it looks like nothing like a geometric phase.
Okay, I see. Thank you.
So where's the non-commutative resolution?
It's a good question. So the reason is called a non-commutative resolution, I should have said it, is because of the remark 3. Because I started with a singular space, right? The singular space was the double cover.
Which is your Y, or Y check, or...
Y check or Y, I mean, this case doesn't matter at this point. So let's say Y check. So it's a singular double cover, and I wrote for you a model, that's the physical part, but I claim that the category of B-brains, or the category of chips, what will replace the category of chips on that singular space, will be this, like a derived category of modules of an algebra, modules of a non-commutative algebra. So because of this form of the V-brain, is why it's called non-commutative resolution. Because it's the category of chips I replace it by the category of modules of a non-commutative algebra. In this case, this Clifford algebra.
So is this Clifford algebra like some non-commutative deformation of Y check? Can I say
Not that I'm aware. It's not in that sense that it's a non-commutative resolution. It's not in the sense that I change Y from being a commutative variety to a non-commutative variety. If you want the non-commutative variety, I'm replacing Y or Y check 4 is that Landau-Ginzburg model, which is not geometric at all, right? It's a Landau-Ginzburg model. So that's like the non-commutative. But the non-commutativity comes from the fact that the the V-branes on that models are given in this form. It's not just ordinary chips over space.
So, why is it so strong evidence about annihilation of this partition function? Why do we expect that to always work?
No, this is evidence. I mean, this is evidence. You still haven't shown, for example, homological mirror symmetry or any of these fancy words. This is just evidence that because the periods, if you compute the classical periods on any Calabi-Yau variety, they no matter along which gamma you integrate, they all satisfy the same differential equation, right? They all satisfy a differential equation which is common to all of them, which is this GKC equation, or Picard-Fuchs for the most common used name, let's say. So if I claim something is equal, the minimum thing I can do is to show that they satisfy the same differential equation. Maybe what I should have emphasized, if you haven't seen this, is of course when I said this annihilates this, this is for all choices of B.
Okay, so we are out of time, and let's thank Master again.